deviant.
So thanks everybody for coming. So it's my pleasure to welcome Jugal Garg to give the closing talk today. Jugal is a faculty member in the Department of Industrial and Enterprise Systems Engineering. He spent a lot of time close by. He did his BTech and his PhD from IIT Bombay. For his PhD, Jugal showed a breakthrough result on computing equilibria and what are called bimatrix games, which are basically these two-person games which formed, the cornerstone of algorithmic game theory for a long time. He has since worked on many problems, including fair division. EFX is one of the big open questions in fair division, and Jugal will impact EFX. I should mention that he has a lot of awards, best paper awards, teaching awards. I will not mention all of them. You can look them up on the web page. I'm just glad that he's here today to give this talk.
Thank you for the kind introduction, and thank you, Kavita and Raghu, for hosting me here. And hello, everyone. So in today's talk, I'll talk about allocation problems dealing with chores. And this is the joint work with my two students, Aniket Murekar and John Quinn. I can move, right? Okay, so let's start. So please feel free to interrupt and ask questions. So allocation problems we deal in our day-to-day life. For example, we want to divide inheritance among multiple people, course allocation, food distribution, chore distribution, task scheduling, and so on, or paper review assignment. And we can divide these problems into maybe at least two categories. These are the goods, these are the goods, and let's say these are the chores. Of course, I don't know, the course allocation, the good or it can be different for different people. So goods means that you want more of them, and chores means you want less of them. Okay. So in this talk, we will be dealing with the chores problem, and the setup is as follows. So we have a set of n agents, and we have a set of m chores. And these chores are indivisible because we are talking about discrete setting. So indivisible means each chore can be assigned to exactly one agent. So you cannot fractionally divide among multiple agents. It's not like that, like half of the chore, this agent does 1/3 this. So one chore has to be assigned to exactly one agent. And we will assume that agents have this utility or the cost. If you're more familiar with the cost, I will call them disutility. So they have disutility and they have additive disutility. This additive disutility means that di of xi, di is the disutility function of agent I, and xi is the bundle of chores you are giving to agent I. Then this is like summation over all chores in xi and diz, where diz denote the disutility of chores to agent I. And without loss of generality, I will assume that diz is positive. So 0 you can handle. So not a big deal. So let's say the disutility is positive for every agent and every chore, and agents have additive disutility. So this is the input to the problem. So we have n agents, we have n chores, and actually diz is the only input, right? Diz is the disutility, and the goal is to find a partition which is fair. We want to partition the chores among agents, and we want to find a fair partition. Now the question is, what is fair? So one quintessential notion of fairness is envy-freeness, where we say an allocation X is envy-free if for every pair of agents, you take any pair of agents, any two agents, no agent envies another agent. So that means that di of xi should be at least, or at most di of xi. So you see, I am putting only I here. So agent I, this utility from his own bundle xi should not be more than the disutility of I for any other bundle. And this should be true for every agent. So this is envy-freeness. So everyone is happy with their own allocation. No one envies, no one wants any other agent's allocation. So this is a very good notion, right? But the question is, can we always guarantee envy-freeness? As you can guess that we cannot guarantee envy-freeness is a very strong notion in the discrete case. For example, suppose these are the 5 chores and we need to divide among 2 agents, and let's say every agent has the same disutility for every chore. But no matter how you divide, someone has to have at least 3, right? And whoever has 3, let's say this Alice has 3, and she will envy Bob because Bob is doing only 2 chores. So envy-freeness cannot be always guaranteed, and
That's when you hire a new faculty.
Huh?
That's when you hire a new faculty.
So we need to refine it. So it's too strong for discrete setting. Yes.
Sorry. So generally, when you have chores, you won't have goods. Like this is
Just chores.
and this nice question. Fundamentally, why can't you just do something like change all the utilities to negative and work with it?
It's the same thing. It's the same.
It's the same thing.
Yes, something. I'm just talking about disutility or cost. So if you are talking about negative, you want to maximize it. Here we want to minimize. It's the same thing. Any other question?
So I mean, all of this can be phrased as
Yeah, it's the same thing.
Wait, but I thought EFX would be different.
No, he's saying that you just use the utility and make it negative numbers.
Yeah, but if it's goods, you take something out from your.
It's not goods, it's still chores. But you want to treat it as a utility. Then it is
So far the definition doesn't matter if it's goods or.
Then what do you define here?
Yes.
I'm not even a plan, so it's like yeah, so it's the same thing. I think what I understand it's the same thing. You are talking about chores. Chores means you want less of that.
Yeah.
You will prefer having nothing. You don't want to do anything, right? But we need to divide all the chores. Okay. So this is the definition of envy-freeness. So it's very too strong for discrete case. We need to refine it. So the most compelling refinement of envy-freeness is for EFX, which is envy-free up to any chore. So we know that like we cannot find envy-free allocation. So Alice envies Bob because Bob has only 2 chores. But if I remove any single chore from Alice's bundle, then the envy should vanish. So for example, if I remove this chore, the envy should go away. If I remove this chore, the envy should go away. And if I remove this chore, envy should go away. Any single chore should vanish the envy. So this is the EFX. So you just want to remove one single chore. Either this agent does not envy any other agent, this is good. But if someone envies some other agent, the envy should go away if I remove any single chore from the envied agent's bundle. So mathematically for
Envious agents.
envious agent. Thank you. So mathematically we say X is EFX for every pair of agents for all chores in Xi. Di of Xi minus C should be at most EFXs. So I'm just using minus C here. So this is the requirement. So this is the definition of EFX. Is it clear? Any questions?
That's a good question. So, how about you change this to removing some chore from my bundle?
I will come to that. We will have slides on that. But right now, that is called EFR. I will define that later. But this definition is clear, right? For every single chore, the envy should go away. This is like almost envy-freeness, right? This is like very strong notion of EFX is a very strong envy-free notion. And the question is, can we always guarantee EFX? And the answer is we don't know yet. So this is considered one of the major open question in discrete fair division, whether EFX always exists or not. So we don't know yet. So since we don't know, so the progress is made on like special cases. So we know that EFX exists for 2 agents. EFX exists for 2 types of chores. Two types of chores means there are only 2 chores with multiple copies. Right, you have multiple copies of 2 chores. So it exists for that. Ordered instances means that everyone has the same order of preferences. Like everyone thinks that this is the most distributed chore, then the second most distributed chore, and so on. And when the number of chores is at most twice the number of agents, and maybe there are maybe one or and then.
When you say all of this exists, it means for all choices of the disutility function DIs for all
So like for two agents, you can take any DI there. So only there are two agents.
Okay, so for
For all instances of this class, it exists. Yes. So exist means it should exist for every instance. So it exists when there are only two agents, and it exists for two types of chores. Oh, yeah. So two types of chores means like there are only two chores with multiple copies, so two DIs.
Sorry, M is the number of chores.
Yeah, is the number.
The M at most 12 thing subsumes the two types of chores, isn't it?
No. There are two n chores, right? There could be two n chores, and every chore can have a different DI here.
Oh, you mean for each agent?
Each agent it can have a different DI value for two n chores. It's a different case.
And
Yes.
lithographic preference is also considered in this ordered instances.
Okay, let's talk about it later because we need to define lexicographic.
And we are still dealing only with additive this and
We are talking about additive later this today. In my entire talk, I will be only talking about additive. And there may be a few cases which I may be missing, but you can see that we are very far away from the general problem. These are very special cases.
so these are the cases for which these are the classes for which we provably know.
Probably know that EFX exists.
And it's it could be the case that actually EFX is true for all additive.
It could be true. We don't know any
We
counterexample.
don't have a problem.
we have counterexamples when the function is not when the.
Counterexample means you give a one instance where it does not exist. That's it.
So no, so for instance, if your this utility function is no longer additive. that-
For super additive, it is known that it does not exist. Super additive, it is known. There is a simple counterexample for three agents.
Yeah.
For which does not exist, but I am only talking about additive. So it gives very like interesting opportunities for three agents we don't know. It is considered already like just for three agents considered a big question.
So what is the third thing here? Ordered.
Ordered means like you have like you can order the chores such that like everyone has the highest distributed value for the first chore. It's the same order. The number may be different, but the it's the ordinal preferences and the same order. So for three agents, we don't know if it exists. And if Diz just takes two values, we don't know. It's called Y-valued instances, where Diz can only take two numbers, A and B, we don't know it exists or not. So these are, I think, two interesting open questions which I think I like.
What is DIJ?
Diz is the distributivity.
Of agent type to
Oh,
So this AB is like the same.
AB is the same for every agent.
Across it.
Yeah, it's just a two numbers for all Diz. Just two numbers.
Can we assume without loss of generality is 0, 1?
You can assume 1 and k.
1 and
0, I am assuming Diz is positive.
so 1 and 2 can
1 and 2 you can.
matrix entries will be either here.
So 1 on 2, it may be 1 on 2. Recently, someone proved that 1 and 2 it exists. So any values of NT. Discrete means like the bi-value distances means any two values of NT. But you can scale them because it's a scale-free problem. So you can make one like A and B are positive, so you can make one entry 1 and the other entry, let's say B over it. It's the same thing. So 1k. So 1k is the general thing. So you want to show for every k. That is the bi-value distributivity. It should work for any A and B. A and B is not fixed. For any A and B, it should work. Then we say that EFX exists for bi-value distributivity.
Is there I don't know, is there like a complete sub-problem in the sense that if it is the case that EFX does not exist, it will not exist for this type? Is there any such statement? No.
There is no answer to this one. Probably self-reducing. I think it's like many, like some people believe it all. It exists for like they think that it should exist for all like, and something that maybe does not exist. So it's not clear. Even for additive, right? It's like
I mean, it's not like we know that if at all EFX does not exist, it will not exist for 4 agents, or there is always a reduction from.
okay. So it can happen. Okay. So I think this is a very good question. It can happen that it exists for 4 agents, but it does not exist for 3 agents. It can happen. So it's not like that. If you can prove that it exists for 5 agents, then it will also prove that it exists for 4 agents.
No, I'm not expecting it.
Yeah, so it's like, or maybe it may exist for 4 agents with and 10 goods, but it may not exist for 4 agents with 9 goods. So anything can happen. There's no such relation we know. Okay, so
What is X? Stand for here. X is the allocation. X is the bundle.
X to the partition.
X is the bundle,
The X
partition.
there is a partition.
Okay.
I is.
Yeah.
I was bundle.
No, the X and the EFX.
Oh, X means you remove one.
X
EF means envy-freeness.
Up to.
Envy-freeness up to one.
Oh, okay.
One.
So, just curious, how long has this notion been around?
EFX was defined in 2016. First time. And since then it has been extensively studied. Like every day you will find one or two studies in paper on archive, which I am also not keeping track of it. So it's been like okay. So another thing to consider is partial allocation. So that means that you don't allocate all the chores. You allocate, for example, if you don't allocate anything, it's EFX, right? No one has to do anything, it's EFX. So the question is, can we, how many chores we can allocate such that we guarantee EFX, and how many chores, like we want to minimize the number of unallocated chores. And we don't know any non-trivial guarantee. So that means like maybe you can give one chore to each agent, or maybe, so that will be EFX because you can remove one chore from your bundle, but we don't know any.
So that's like a subplot, right? You're just taking off one chore from the list. And you're not allocating it to anybody.
No, I am saying that like we want to find an allocation, partial allocation. Partial allocation means you don't allocate all the chores, but we want, maybe some chores are unallocated.
Right.
But whatever we have allocated, it is EFX.
Yeah, but that's like the same problem with one chore.
No, but you do not know which chore.
But you don't know.
But it is like, you just try the EFX.
Yes. So we don't know any non-trivial guarantee here. And in the case of goods, which I'm not defining, Kavita and others gave very celebrated result. They proved that EFX exists with at most n-2 unallocated goods. So here the number of unallocated goods does not depend on m. It is just n, the number of agents. And we don't know any such result for chores.
For chores, you are aiming for getting less than 10 chores as charity.
Anything like game over anything, nothing is known.
So, for example, sorry, just to be sure that I understand. So suppose you found that there are only two chores. Oh, that's not.
M chores are given, right, initially.
Okay, just curious. What is the analog of charity in this city?
Which charity?
I mean,
There is no charity here.
No, I mean, for goods, the thing that you are not allocating is often regarded as charity.
Actually, yeah, I should ask Kavita, right? Charity guarantees, that's the title of this paper.
Lethargy.
If you manage to solve this problem, I suggest you call it outsourcing.
Okay, so let's move on. And another popular approach is to consider approximation. So where like where you consider EFX, but you multiply the factor alpha here. So what is the alpha EFX? So X is the allocation, X is alpha EFX. For every pair, this is the EFX, you just multiply by alpha here on the right hand side. So if alpha equals 1, then it is EFX. And the question is for what alpha we can guarantee this alpha EFX. And we want alpha to be as small as possible. Okay. So this is the notion of alpha EFX, and there is a sophisticated algorithm which proves in 2022, which proves that n square EFX exists. And more recently, we can show that 4 EFX exists. And in this talk, I will, in the rest of the talk, I will give you an overview of its proof. So this is the result I want to show you. So the definition clear. So we will just like further relax. So EFX by putting alpha here, and we want to show that like when alpha equals 4, we can find an allocation X. Okay, so the problem is clear. So this problem, yes.
All of these for goods and chores, the definitions are similar.
No, the definition is different because here you remove a chore from your own bundle, but in the goods you remove a good from other.
EFX definition change.
Yeah, EFX
That's why they had the comment in the previous. That is, the corresponding result of theirs is not known.
Right.
Okay.
Because chore you remove from your own bundle, but in the goods case you remove a good from other agents bundle. Makes sense, right? And also like in the goods case goods case, anyway. So for EFX, I want to show you. Okay. So this problem we approach by another major open question in fair division, which is the existence of EF1 plus PO allocation. So let's first understand what is EF1 and what is PO. So what is EF1? So this is the in EFX we want NB to vanish after removing of any single chore. But in EF1 we just want one chore. If you remove the worst chore, the one chore, if NB vanishes, then we are good.
This is the question.
This is the question, I think, yeah. So if I remove my worst chore, then I don't envy the box bundle, then this is EF1. So let's say this is the EFX where we put for all chore. For any single chore, the NV should vanish. Here we just want there exists one chore, the NV should vanish. So the difference is only in this quantifier. From for all to I just put there exists. Okay, this is the only difference between EFX and EF1. So this is EFX, this is EF1. And we can easily see that EF implies EFX, EFX implies EF1. So is the EF1 is a weaker refinement of NV-freeness. What we know about EF1? EF1 always exists, and this is worked by Umang and others through a very nice and simple algorithm. They prove that EF1 allocation always exists. And we don't know anything about that. So EF1 allocation always exists, but EF1 allocation itself is not very interesting. We want some efficiency also. So for example, suppose these are the two chores and two agents, and let's say this is the disutility 100, 100 and 1, 1. And this allocation, which looks not good, right? You are giving the top chore to the top agent and bottom chore to the bottom agent, and both are having disutility 100. And we can easily reallocate them like this. So this is EF1. In fact, EFX, because there is only one chore. So, but this allocation is not good because you are like not efficient. This is not efficient. This is the allocation ideally we want. So we want an allocation which is a fair and also efficient. So let me define the definition of efficiency, which is Pareto efficiency, which is a standard definition of efficiency. So we say that an allocation X is Pareto optimal if there is no allocation Y where some agent is better off in Y than in X and no agent is worse off. So that means like if you cannot improve this allocation. A Pareto optimal allocation means if you want to improve, that means someone has to suffer. So ideally we want EF1 plus PO allocation. We want an allocation which is fair as well as efficient. So let's say EF1 plus PO. Yes. What we know about existence? Again, some problem we don't know yet. It's again another major open question in discrete fair division, whether EF1 plus PO allocation always exists or not, we don't know. And again, the progress is happened on special cases. So we know that EF1 plus PO allocation, Y valued instances A and B, which are two types of chores, three agents we know, three types of agents, and maybe there may be a few cases. And you can see that like we are very far away from the general case, very special cases. And this gives like interesting open question, like four agents we don't know, and like bi-valued we know, but tri-valued we don't know. So this is like one way. And another way is again the approximation, but now let me also relax the 1 to k and define a more general notion of EFK and PO. So this is EF1. We remove one chore. Now let me allow to remove k chores. I can define EFK. So let's remove k chores, any k chores. If there exists some k chores, if I remove them, then the NV vanishes, and also multiply this by alpha on the right hand side. So this is alpha EFK. And we want alpha and k to be as small as possible. When alpha equals 1 and k equals 1, this is EF1 plus PO. The question is what we know about alpha EFK plus PO. Clearly alpha EFM plus PO is trivial because you give all the chores to one agent.
Alpha is one, why the PO?
That's not pure.
No, this is EFK, alpha EFK. Alpha EFK. It's nothing to do with PO. This is just PO is clear. PO is the yeah. So this is the definition of alpha EFK where you remove k chores. some k chores. If you remove then the disutility of the remaining bundle is at most alpha times the disutility of other bundle. So this is the alpha EFK, and we want alpha and k to be as small as possible. So EFM plus PO is trivial. Like we can give all the chores to one agent, and it will be EFM plus PO, and we can show that any EF1 plus PO exists. So, and also we can show that two EF2 plus PO exists. So we don't know, yeah. So these are the only thing we know here. In fact, this is a slightly strengthening. We can prove that existence of PO allocation in which every agent is either 2 EF1 or 2 or EF2. But let's not worry about this. So this is the result we can prove, and we will I will show you how to get 2 EF2 plus PO. And once we have 2 EF2 plus PO, we will use that allocation to get 4 EFX. So first we get an allocation which is 2 EF2 plus PO, and then we will start from that allocation and then get 4 EFX. So this is the approach. First we get 2 EF2 plus PO. Questions?
Is the second part general if I have alpha EFK plus P or can I get alpha times K EFX or something?
No.
It's for this.
Like in fact, it is not clear that if you can get EF1 plus PO, which is also 2 EF2 plus PO, right? So
No, I'm saying suppose there is an allocation that is alpha EFK plus PO. Does it imply an alpha K EFX? No?
no. So you are multiplying 2 by 2, right?
Yeah.
Okay.
So EF1 plus PO and EFX are incompatible.
Yeah, because EF1, EFX, we are not talking about PO, right? So PO is a separate type of guarantee, right?
Okay. So the question he's asking is if EF1 plus PO exists, does EFX exist?
No, I think it's just saying like because I'm 2 and 2, right? It's multiplying 2 vector here, 2 here. And I'm
Exactly.
getting 4 EFX. So
Exactly.
alpha and K, alpha K EFX. Yeah, so no, it's not like that.
If you want me to be fancy, I can say
So
alpha
it's-
to the K.
I think the 4 is like, I think, yeah, that's because we started with like 10, we got first 10, then 5, and then 4 actually. And I think 4 is the best we can get from this approach. Okay, so let's see how to get 2 EF2 plus PO. Okay, so the difficulty here is to get PO. So if you only want PO allocation, it is easy because like you just minimize the disutility, it gives PO. If you want only EF1, it is also easy through Oman's and others algorithm. There is a round robin and envy cycle based algorithm, simple nice algorithms which guarantee EF1. But if you want both EF1 and PO, it becomes non-trivial. The reason is even like checking whether an allocation is PO is co-NPR. So you cannot even certify that like this allocation is PO. This is the main difficulty. And so PO makes the problem very hard. And how we deal with PO? We use competitive theorem. So competitive theorem guarantees fractional Pareto optimality, which you can check because it's a fractional Pareto optimality, which is stronger than PO, but this is the only way we can guarantee PO. Okay. So what is competitive theorem? So this is competitive theorem. So let's say we have like we have a setting where agents want to earn some money. Let's say EI money agent I wants to earn, and chores are attached payments. So each chore has some payment. Let's say if you do this chore, it will pay you $5. If you do that chore, it will pay you $10 and so on. So chores have attached payment, and each agent has a earning requirement that agent I wants to earn, let's say $100 or $5. So every agent has their own earning requirement, and chores have attached payment. The chores can be fractionally allocated. So in the competitive theorem setting, chores can be fractionally allocated. So one chore you can allocate to different agents, half of the chore to one agent, 1/3 to another agent, and so on. So chores can be fractionally allocated, and agents want least disutility value subject to earning. So each agent wants to earn, let's say EI dollar with the minimum disutility. Because like with whatever payments you are assigning, you want to you want to do the chore, the bundle of chore, which gives you the minimum distributivity and gives you EI dollar. So so formally, let's write it. So formally, Y and P is completely round. Y is an allocation. P is the payments. It's a completely round if you allocate all the chores. Because if you don't allocate anything, then it is completely. So you need to allocate all the chores. And optimal bundle means each agent should get the least distributivity bundle. So that means that Yi is the bundle agent I is getting should be the minimum possible distributivity subject to the earning constraint. Because like agent I wants to earn EI dollar, so Yi is the amount of chores agent I is doing, Pj is the payment of chores. So you multiply Yi times Pj, this is the earning from chores. You sum over all chores, this is the total earning for agent I, it should be EI. And subject to this, among all possible bundles, you want to get the bundle which is the minimum distributivity.
This seems very strong.
DIY. So this is the notion of competitivity. Is it clear?
Yeah, but still, we want to, so suppose both of them minimize are the same, so. what do we do?
Is the definition of competitivity clear?
No, Jugal, so these PJs are not given, right?
No, this is you need to find. I only input is the DIJ and EI, right?
Exactly. So in your case, for example, the payments would be.
Oh, this Y and P you need to find. I give you like only EI is given.
I see.
EI is given, P is a variable. EI is given and DIJ is given. So only the earning requirement is given and DIJ is given. And the question is find Y and P allocation in the payment such that you allocate all the chores. Y should be a kind of allocates everything, market clears kind of clear every chore and also every agent gets this thing. Okay. So why this is it? So let's rewrite this optimal bundle condition. So what we want is like let me reformulate it again. So for every chore is allocated, every agent earns EI dollar. This is the earning. And this condition, the minimum distributivity, you can translate into this MPB condition, minimum pen per work condition. So that means that DIJ over PJ. So let's first understand what is DIJ over PJ. DIJ is the distributivity of agent I for chores. PJ is the payment of chores. So DIJ over PJ is what is the distributivity for $1 earning? This is like for $1 you want to earn. What is the distributivity? You have to suffer if you do this chore. But if you want to do the bundle with the minimum distributivity, you will only want the chore which is the minimum rate, right? From $1 earning, what is the minimum distributivity possible? So you only want to do those chores for which the rate is the minimum. So you want the allocation on minimum pen per buck allocation.
So it's in comparative equilibrium, there is no notion of envy that you brought in, right?
No,
Envy,
I will come.
currently, there is no notion.
This is the comparative. I will come to envy. Of course, we need to relate to envy free and this thing. But this is the thing comparatively done that every chore is allocated, every agent gets their requirement, and they are getting this requirement with the least distributivity bundle, and least distributivity bundle gives you this condition. Okay. So this is comparative. This is a strong condition. Why should there exist such an allocation? It's not clear, right? Yeah. So we will come to that. But so far so good. I have defined this concept comparatively now, and this is the constraint. Why this is interesting? This MPB condition implies PO. So if you give me any allocation and some payments, and you can prove that this satisfies this allocation, satisfies this condition, this implies PO. This is second welfare theorem. So anyway, I will not go to the proof, but this implies PO. So you just need to give me an allocation, and if there exists payment for some variable P which satisfies this condition, then it automatically gives you PO. So we are very good. We just like if you have competitive theorem, it automatically you have Pareto optimality. So Pareto optimality is free from competitive theorem. And suppose we say EI equals 1. Everyone has to earn the same $1. Then it gives envy-freeness. Why? I need to earn $1. Raghu has to earn $1. We are facing the same payments, and you are buying the least distributive bundle for your distributive function. I am buying the least distributive bundle for my distributive function. So why would I envy you? Because if I envy you, I could have asked for that bundle, right? So there is no envy. So we can set EI to $1, and then this will give you EF. So competitive theorem implies envy-freeness plus Pareto optimality. So this is very good, right? Envy-freeness Pareto optimality we get just from competitive theorem. The only problem is the allocation is fractional. So now the question is, the approach is, this is like competitive theorem with equal earnings because we will set EI equals 1. So the question is, we start with such an allocation. Suppose we can find a competitive theorem with equal earnings. So why is such an allocation? Why is EF plus PO? I just showed you is envy-free plus Pareto optimal. And now the only problem is y is fractional. Now the question is, can we round y so that we get some EFX, EF1, EF2, and Pareto optimality we maintain.
Sorry, so do you like, do you also show any efficiency having like any polytime algorithms, or it just
I'll talk about that in next slide. It's a good question. Yeah. So now the approach is we round y to an integral allocation such that we maintain efficiency. How do you maintain efficiency? Just maintain the MPP condition. So I said if you maintain the MPP condition, it maintains the PO. How will you maintain MPP condition? Because MPP condition just depend on the Dij and the P, right? Because just the ratio of Dij and P. So I can just like suppose this chore is like 0.1, like some fraction is given to this agent, some fraction of this agent. If I give the entire chore to this agent, it doesn't matter, right? This MPP condition is still satisfied. So I just need to round on the support of the allocation, right? Then it is MPP condition automatically satisfied.
sorry, what was in MPP?
The minimum 10 per bucket. This is the MPP. So if you maintain this, then PO is guaranteed. So I just want to round y such that we can easily round. So that means that this chore is given to this agent and this agent. You round it to either this agent or this agent. MPP is still maintained. The only thing that you cannot give this chore to this agent who is not getting anything. Like if someone is already getting some fraction of positive fraction of this, then you can just round it to that, and then MPP is maintained. So we can round such like this and maintain get the PO. For fairness, what is fairness? Now we are rounding is such that, but like maybe we are giving this chore fully to this agent, so we are increasing the earning of that agent. So if somehow we can balance the earning of agents, that will give us the fairness. Because starting everyone is earning $1. So this is what we were started with. But after rounding, maybe someone is earning $100, someone is earning $10. So if we can balance these earnings, then this will give us fairness guarantee. So that is the approach.
So why is going to be the fractional allocation that is there for the chores with the agents? What is P going to be, or you don't care?
P is the part of the competitive theorem. We just forget about it. P is a certificate that it is PO.
It's not complete because you're using it to satisfy this one.
That's for PO we need. It's a certificate for PO. Okay. We are interested in the Y, right? P just certify that it is a PO.
I mean, in the sense that we are not going to hope for a P that is sort of relatively balanced or anything of.
Initially, like EI is $1, right? Summation Y is a PJ is $1, right? That gives envy-freeness. But I'm saying that when you round it, the earning is changing, right? So you round but if you can balance the earning, we round such that the earning is balanced, such that like everyone is earning between $0.50 and $2. Then it is like 4 EF we get. Because like it's already PO. PO means like if we are earning the same, then I don't envy your bundle. If you are earning $2 and I am earning $1, then you are 2 factor away, right?
No. So I'm just wondering that is there a natural like for me to get as close to EFX as possible? Is there a particular type of P I should have in mind, in the sense that
P is not in your control. That's just a competitive theorem, right?
Yes.
Whatever, yeah. First of all, I am not told how to find Y and T. And this is just the approach that you find Y and T through some algorithm which is giving you competitive equilibrium, and then you use the y to round it such that you maintain the allocation on MPV, which implies PO, and you also balance the earning. That gives you some fairness. So that's the approach. Now let's see. So suppose will this approach work? So now we have, let's say, these three agents, and these are the four chores, and this is the competitive equilibrium. It satisfies all the conditions. The competitive equilibrium. These are the payments, and these are the earnings, and these are the whatever. How much, like this agent is like this is the payment is $2. So this agent is like earning $1. So that means they are doing half of this chore, right? So suppose this is the allocation y. This is the allocation.
These numbers on the right are the PJs.
Are the payments. And this is the yeah, this is the how much money they are earning from this chore. So they need to earn $1 each, and this is how they are earning. Agent 3 is doing all the three chores. It's already integral for it. So now, no matter how you round it, how will you round it? So this is already rounded, right? Only this chore you can either give it to A1 or A2, right? That's the only possibility. So let's say we give it to A1. Then A2 is very happy. A2 is getting nothing, right? And A3 is very unhappy. Because when A3 look at the A2's bundle, A2 is doing nothing, and A3 is doing three chores. So A3 is very unhappy. So you can see that we can easily construct examples like this, where no rounding of C will be giving you any alpha here. For any K, for any alpha, it is not possible. So whatever approach I told you, it is not working because of this example. But now, what is the problem with this example? The problem is this chore, right? Because these two agents, their entire earning is happening they are getting their entire earning from this one chore, and this one chore will be rounded to exactly one agent, right? So this is the problem. So let's refine the definition of competitive equilibrium. So let's define the definition of earning restricted equilibrium. So what we want, we restrict the earning that the chore cannot pay more than $1. So this chore, the payment is $2, but let's say the chore is not allowed to pay more than $1. So that means you don't allocate full chore. If the payment is $2, but you can only allocate up to $1. So this is the restriction you are putting on the earning. Because everyone has to earn $1, and if we put this restriction, then it cannot happen that these two agents are spending $2 on this chore. Because the total earning or total money this chore can pay out is at most $1. So suppose we put this restriction. So then the equilibrium will change. Then the equilibrium is like this chore payment is 4/3, but it cannot pay more than $1. Because if you put this restriction, then of course these two agents cannot earn $1 from this. So they need to move to the other chores, right? Because they need to earn $1, and one chore cannot give more than $1. So they need to move to other chore, and this is the equilibrium with that restriction. And you can see we can round it to get good factor. And that's what we will do. So let's define the definition of earning restricted equilibrium. So let's say Pj is the payment of chores A, Yj is the amount I is getting of chores A, and the total earning is Yj times Pj. So let's say Qj is the total earning from chores A, total payout, how much payout chores A is giving, and we want Qj to be at most Cj. Cj is the restriction. Okay. Cj is like can be any number. It cannot pay out more than Cj. It can be different for different chores.
Sigma I Yj is just one, right? Sigma I Yj is just one, right?
No, it can be anything. It can be less than one. Because I am restricting the, like suppose the payment is $2, but it cannot pay out more than $1, so you are only allocating half of the chore. So this is the okay. So maybe so this is the definition formally. So YP is an earning restricted equilibrium if Y is an MPP allocation at P. So we maintain MPP allocation. MPP allocation has nothing to do how much chore you are allocating. It just depend on the D, Ij, and P. So Y is an MPP allocation at P. All agents are earning their earning requirement. So we are not every agent I is earning their EI dollar, but for each chore J, Qj, the amount chore J is paying is at most Cj and Pj. Pj is the payment of chores and Cj is the restriction. So if the payment is bigger than Cj, then it will only pay Cj. If payment is lower than Cj, then it is you allocate the full chore.
It means the chore is not being completely finished.
Completely done. Yes. So some chores are maybe not allocated, not completely allocated. So if the payment is $2 and Cj is 1, you are only allocating half of the chore. But everyone is earning here. And allocation is on MPD. Is this clear? So the only change is this Cj. So I am restricting that like no chore. Yeah, chores they should not get pay out more than Cj.
You haven't yet told us how we get CJ.
No, Cj is the part of the input. P is not part of the input.
No, I understand, but what CJs do we use?
We will come to that. Yeah, I'm not talking. I'm just defining very generally and then we will use particular value of Cj and P. Okay. So question is like we define very nice concept, earning restricted existence. What do you think? It will exist or not? Clearly it will not exist, right? Because if summation earning requirement is more than the total, like this is very simple. If the total earning requirement is more than the total constant you are putting on, then how can you find an equilibrium like this? So at least the earning requirement should be at most the total earning constant you are putting on the chore. But if you put that thing, then we show that like it exists. So and here equilibrium exists if and only if we like it's like complete thing, like if whenever summation EI is less than equal to summation Cj, we prove that it exists. And this is like we use the linear complementarity problem, LCP formulation. We derive an LCP formulation and then do some complementary pivot algorithm. It's a very complicated and involved proof. I will not go into that thing in today's talk. So the theorem is that any EI equilibrium always exists for any EI and any Cz. Only constant we need is anyway. This is like sufficient. We need that condition. Now, what about computation of EI equilibrium? Even the computed equilibrium without earning restriction, because this is like even a more stronger notion. The set of computed equilibrium is non-convex and disconnected. It exists. Computed equilibrium exists, but the set is non-convex disconnected, but pitas exist. So F pitas exist, so we can compute them approximately. For ER equilibrium, we can get polynomial time algorithm for constantly number of agents, and when there are number of agents are fixed, but we don't know how to solve computation for general case, even approximately we don't. Any questions? Seems like okay. So let's. How much time I have?
10 minutes.
Huh?
10 minutes.
10 minutes. Okay, we are going very slowly. So I think we need to skip some slides. So let's say 2EF2 plus PO we can easily get from ER equilibrium. So let me skip that. So approach is like you use the EI earning require $1 and Cj equals $1. This is the values you use and assume that number of items are more than 2n because to satisfy this condition. We get ER equilibrium, then we round ER equilibrium to find, we can round such Y to get 2EF2 plus PU. So let me not go there. So we can just round such an ER equilibrium to guarantee 2EF2 plus PU. Okay. So what we say that like for every agent, if you remove the two worst chore, the total payment is at most $1 and everyone is also getting at least $0.50. So that gives the 2EF2 guarantee. So let me skip this part. How we round the Y to get 2EF2 plus PO. And let's come to more interesting thing. Now we have 2EF2 plus PO allocation. So now I'm talking about 4 EFX results. So we start with 2EF2 plus PO allocation. And we can also prove that there are like the 8 chores are like the chores which have payment more than half. Because like Cj I was putting half. Cj so the chores which are not fully allocated. So H is the set of chores which are not fully allocated. These are the 8 chores and like 2EF2 plus how many such chores will be possible? 2n at most 2n. Because their payment is like more than half, and the total 2n chores.
So the situation is, I mean, like, each chore is allowed to, the maximum earning it can give you is half, isn't it? That's the setup.
Hmm.
Okay.
So the chores which have payment more than half is at most 2n.
Okay.
And so we have 2 EF2 plus PO allocation, and each agent has either 0, 1, and 2 H chores. These H chores are very difficult because, like, maybe the payment may be maybe $1 billion, right? Because whoever gets this chore, it's like very high disability, right? Because we need to round it. Maybe fractionally it was not given fully, but when you round it, suddenly it has to be given fully, right? So these H chores are the most difficult thing to handle. So in this allocation X, each agent can have either 0, 1, and 2 H chores. The total H chores are 2n. So this is kind of the allocation. These are the low value chores, L. Low value chores, low paying chores means less than half, and these are the high paying chores. And the high paying chores are at most 2n, and every agent has a 0, 1, and 2. And we also have this condition that if you remove 2 chores, then the total earning is at most $1. If you remove the 2 high paying chores, and every agent is earning at least $0.50. This is the condition we have from 2 years. Okay. Now let's see. So let's say we first handle the 0 H chores. Suppose the agents which have 0 H chores, they don't have any high paying chores. So it's very easy. The agents who have 0 H chores are already for EFX. They are already happy. They don't envy any agents. They are already for EFX because of these conditions. I will not have time to prove this, like, but it is like clear, like if you don't have any high paying chore, you are very happy actually. Because like everyone is earning at least $0.50, and so that already implies that you are not here. So for it. It's like 4 EF, not even.
So P minus 2 means that there exists 2 chores.
You remove the worst 2 chores.
Worst 2 chores.
And then count the payment of the remaining one.
Yeah.
So 0 H chores are very good. Now let's see what to do with 1 H chore. So the 1 H chore, the agent who has 1 H chore may not be for EFX satisfied. So maybe this is the agent I who has 1 H chore, and he is not for EFX because he has like these low paying chores, and this is one high paying chore, and he envies some agent L for EFX. Then what we do? We swap the chores. So what we do? This is we take the L who I envies the most, because for L's bundle is the best bundle. Among all agents, L's bundle is the best bundle for I. So we pick such L and we give all the bundle. L can have 1 H chore or nothing, whatever. So we give the entire bundle to I. And L will only get the 1 chore, the high paying chore of I to L. So this is the reallocation we do. So L just gets one chore. Because this is the chore which is the problematic for I, we give this 1 chore to L, and everything else I keeps. Is it clear?
No, you
So this is the worst chore, that's why. So this L is, here we lose P, because we don't care about P all of this, MPB condition. So this L is happy because L may have a very big chore, but it has only 1 chore. Which he can, so EFX means you can remove 1 chore, right? It can. So L is happy, and we can prove that I is also happy. So after this chore swap, we can prove that I is for EFX and L is anyway EFX.
So all these go to ice bundle.
All is go to I. So it's not difficult. So what I is happy, I is for EFX and L is EFX. Now the question is, can we continue like this? We keep finding I and L and keep doing this such that finally we enter with 4 EFX. And it doesn't work. The reason is envy can redevelop. We fix the envy of I, but when you are swapping other I prime and L prime, then I can redevelop the envy. I is now 4 EFX for every agent. I is happy, but I can become unhappy later. So it can be a problem, cycle problem. So envy can redevelop, and another problem is that I have not told you how to handle agents with 2 chores, which are the most problematic. So what we do? So first we look at the H chores. This is like coming from the competitive theorem, the ER to the ER theorem. We first reallocate these 2n chores, the H chores. How many such chores are there? At most 2n. And if you remember, If the number of chores are at most 2n, there exists EFX allocation. So we find the EFX allocation of these 2n chores, at most 2n chores. There exists such an allocation. And then we just reallocate them. This is the reallocation. And then this reallocation is a very nice property that agents with 0 and at least 2 chores are for EFX. So we have fixed the NB of 0 chores, and this reallocation can give some agent more than 2 chores also. This is like this can be anything, right? So the 0 and at least 2 chores are already happy with this reallocation. It's okay. Intuitively, it is clear because for H chores they are EFX, and this is like just nothing. These are like kind of very least distributed because these are the most problematic chores, right? So these are not adding anything to their disutility. So the high paying chores are already EFX, so which is good, and these are not adding anything. So this implies that the 0 and at least 2 H chores are already for EFX. The problem is the 1 H chore. So the agents will have 1 H chore, and we again do the same thing. We do the IL swaps, and here the only thing is that we need to worry about these IL swaps has to be performed in a carefully chosen order to not redevelop the ND of IL. You cannot just arbitrarily take IL if there are, you need to do in a particular order to prove that NB will never redevelop, and finally it will converge to 4EFX allocation. So I think that's all I have to say. This is the summary, and you can see tons of open questions. And I think I'll just end up with, I've already told you about these 2 questions. So let me stop here. Questions. And I will be available. I'm happy to talk more after.
Usually for getting approximate EFX, there is a template that they follow, right? Like you get some allocation, you satisfy some properties, and then you run the difference algorithm. So here.
Different algorithms EF1 gives, right? Gives EF1.
But I mean, initially you satisfy some properties, and then on top of that, if you.
That is for goods usually, right?
For goods, yeah. So can we do the same here after allocating the H chores?
It doesn't give any approximation EFX actually. That's the problem. So you are right. For goods, it gives half EFX. For where just the simple algorithm gives you half EFX, right? So for chores, doesn't give anything. It doesn't give any approximation for EFX. That's why n square was the celebrated result. Yeah. Because the first time they could prove n square EFX in like 21, 22 factors.
The market like they give you 2 steps from the first step to the second step. Like you didn't really use the fact that you.
Very good. Yes.
You have
So
a
we use this upper and lower bound.
Yeah.
So I think yeah. So let me rephrase this question. Like suppose we start with any 2 EF2 plus PO location, will we get this? No. Any 2 EF2 plus PO will not give you a 4 EFX. We need those upper and lower bound. We need more properties on top of that. So we don't need market equilibrium. We just need upper and lower bound of the initial allocation to start with. So can we do? Yeah, can we? It need not be market equilibrium. But using market equilibrium, we prove additional results.
Sure.
Like for bivalue disutilities, we can just round on the MPV and get PO properties. But that's very good question.
Then other weaker questions like I don't know, EF2X type thing, in the sense that
EF2X.
I mean, in the sense that my NG goes away if I drop off the top
Least
two.
two.
Or
Whatever.
the first two.
Best two.
Yeah. So other like
Nothing in. I think for goods, I think EF2X recently there is a paper which proves that 4 agents it exists. EF2X.
for 4 agents.
4 agents goods, yeah. Additive goods.
So for chores, even for 3 agents. So it seems that for chores become much harder because the technique for goods there are 2-3 standard techniques for goods that don't extend to chores. That's the difficulty in chores. So that's why we are going through this ER equilibrium, and we need lower and upper bound, and so like require more properties. Yes.
The very vague question. So there are some connections known between some sort of these game theoretic notions and like the class PPAD or something, and you know that this is exactly characterized by some like local search and gradient descent, and there was a famous result, right? PPAD is CLS intersection.
CLS equals PPD intersection PLS.
Sorry, maybe this question is not well formed. Is there any way to sort of connect these sort of game theoretic notions to existence of solutions in like gradient descent, local search sort of areas?
And they're like,
Like for algorithms, right?
And they know the total problem, like you know that the solution.
PPD means it's like already, your even existence is not clear. There are two problems, existence and then later computation.
Yeah.
So I already showed 4 EFX existence. We don't know how to find it in polynomial time. That's open.
Maybe I was wondering.
Because the difficulty is computing ER equilibrium. The rest of the rounding is simple polynomial time.
I was wondering if existence of EFX can be connected to existence of some non-game theoretic.
Yeah, I think we don't know anything like that, but yeah.
So for two agents, what's the, I mean, do you know the algorithm or?
For report EFX.
EFX chores. I mean, is it similar to goods? No.
Yeah, divide and choose will give you EFX.
So like.
One agent
for-
divides
Yeah.
is best.
So for goods, we know that it exists for 3 agents, and there they have used for identical valuations, they have used this algorithm called plot rough garden. Does it also work for chores?
Plot rough garden works for choice, yes.
But still, I mean, for n equal to 3 agents, we don't know. Okay.
When you say they, you mean.
Yeah.
Yeah.
Any other insight or any connection?
I don't understand why chores are difficult to solve than goods.
Because I said like the techniques like these are like standard thing, envy cycle, they don't extend to chores.
Not difficult, but different. Let's work on goods for a long time, not for chores.
Right.
Yes.
Or maybe yes.
So does this extend to mixed items also?
I've not thought about mixed items, but this for EFX.
Yeah, then we have to.
Sorry, what does mixed item mean? It's not indivisible.
No, it's like you have goods and chores. You have
I think. Oh, okay.
mixed actually. You have some goods, some chores. Something
And then
like
we
that.
have, there we talk of half EFX, it's
Ah,
not here it
okay.
becomes 2 4.
I've not thought about that, yeah. Probably nothing is on for next of course.
Okay, you take one question offline. Okay, that's time to go.
No,